In this section, we're going to be looking at the inverse of a matrix, how to define it and how to compute it. So with that in mind, let me go ahead and start with a definition. An n by n matrix is invertible if there is a matrix C such that A times C is the same as C times A, which is the identity matrix, the IN identity matrix. Remember, that is, when I write IN, that means that's the n by n identity matrix. And we write C equals A inverse. So notice that it has to work on both sides when you multiply on the right or the left. You may have remembered that we did something like this, where we had a CA was equal to I, say N, but then we had an AD was equal to I, say M. Well, if the same matrix has to work on both sides, that means that here C would have had to have been something, I'll call it P by N. But now if the same C is also to work on the other side, then we already know that A has, well, let me do this. A is an N by N. So C on the other side, being a P by N, means that the P, remember, the columns of A equals the rows of C. So that will force P to also equal N, and then we'll have that C is N by N as well. And also there was something to do with, I had a couple of problems the last couple of videos where one of these situations showed that M was less than or equal to N, and the other situation showed where the inequality was reversed, and that forced M to equal M. And so what this all means is that we're only going to define inverses for square matrices. In the real numbers, we often will write something like this. And then we'll say that 1 over x equals the inverse of x, multiplicative. Of course, x cannot equal 0. You cannot divide by that. A matrix that is not invertible is called singular. And of course, a matrix that is invertible is called non-singular. Immediately we have a theorem. Let A be an n by n matrix. Suppose B and C are also n by n matrices. If CA equals AC equals BA equals AB, and all of those products are the identity matrix, then B equals C. So what we do is we'll start with B, and notice that B equals B times the identity matrix, and then I can swap in AC in place of I sub n, and then I can use associativity, and then BA is also I sub n, but then that is just a C. I love these proofs where you can just do a series of equals. So what do we have here? A can only have one inverse. In other words, inverses are unique. As an example, let me set A equal to 9, 1, 71, 8. And I'm going to let C equal 8, negative 1, negative 71, 9. Now then, when I do A times C, let's see what I end up getting. Well, let's go ahead and do our row column rule. So I take my 971 and match it up with the 8, negative 1. So let's see what happens. 9 times 8 is 72, plus 71 times negative 1. That ends up being a 1. And then when I move over to first row, second column, I'll have 9 times negative 71 plus 71 times 9, which is just 0. As I move on, 1 times 8 minus 8 times 1 is 0. And then finally 1 times negative 71, that's, well, negative 71 plus 72 gives me 1. So I see we get the identity matrix. You can check that CA also equals the identity. So what that means is that that matrix C is the inverse of A. Theorem: suppose A is equal to the following matrix: A, B, C, D, where AD minus BC is not equal to 0, then A is invertible, and A inverse equals 1 over AD minus BC times, what we do is we swap the first and the last items, I guess, from the matrix, and then we put negatives before the other item, before the other elements, and that ends up being the inverse. Proof: show that A times A inverse equals that identity and also equals the identity. You can check that out for yourself, but that's what you need to do to prove it. As a quick example, solve the following system of equations. This is a fairly easy one, but nonetheless, I'm going to use the theorem I just spoke about, and I'm going to rewrite this as the following matrix equation. I'm not going to put it into augmented matrix because what I'm going to do is I know that the inverse of the given matrix, if it does have an inverse, will be the following. I got to do 1 over, now I got to do AD minus BC. So AD, that's 8 times negative 5, minus BC, 5 times negative 7. And then I swap the first and last entries and negate the other entries as such. Let me simplify as much as I can. Down here, I'm going to get 40, negative 40, plus 35 will be negative 5. So I get negative 1/5 times negative 5, 7, 8. Then, when I go back to my equation up here, I can take negative 1/5, negative 5, 7, 8, and times on the left side and on the other side, let me go ahead and put my, so I'm multiplying both sides by the same thing, this inverse matrix. And then we have negative 9, 11. Well, the beauty is that on the left side, all of this stuff, all of it, except for the x1, x2, all of that stuff is the identity 2 matrix. It is I2 times x1, x2. Over here, let's multiply it out. So let's see what I get. I get 45 minus 55. That will be negative 10. And I'll get negative 63 plus 88 will be 25. So when I multiply my negative 1/5 through, I get 2, negative 5. And of course on the left, all I get is x1 times x2. So it makes quick work of that when you can use it. Another theorem. If A is an invertible matrix, then for each B in Rn, the equation AX equals B has the unique solution X equals A inverse B. That's of course what I just did. So start with AX equals B and plug in X equals A inverse B to get And then I can go ahead and use associativity to write my next step. And we see I get the identity, which in this case I sub n. And so we do get b equals b. So x equals A inverse b is a solution. To show that the solution is unique, let W be an Rn with AW also equal to B. Then W equals IN times W. IN I can replace with A inverse A, like so. And of course, I can use associativity. Now W was another solution, so this is A inverse B. So even though I chose W to be any other solution, I see that it's stuck being the same thing as before. So therefore, the solution is unique. Another theorem: if A is an invertible matrix, then so is A inverse. In fact, A inverse, the inverse of A inverse is A again. If A, B are invertible matrices, then A times B is also invertible. And the inverse of AB is B inverse times A inverse. Just like the transpose, it has reverse kind of property going on. If A is an invertible matrix, then A transpose is also invertible. And the inverse of A transpose is the same as A inverse transposed. Let's start with 1. Since A times A inverse is the same as A inverse times A, and that's the identity matrix, we see that A is the inverse of A inverse. So that's not a big deal, because A is a matrix that when I multiply before and after it, I get the identity. That's all that's required for a matrix to be invertible. And from the last theorem, we know that the inverse is unique. Since A inverse happens to do the job, that takes care of that. For a second one, let's take a look at AB times B inverse A inverse. Well, I can use associativity to get the following. And then I'll get A with an I sub n in between it. So I guess you could do that, but then I can reassociate. And of course, A times In is no different than A. And I know that A inverse is equal to I sub n. So that implies that A, B inverse equals B inverse A inverse. So basically what you showed is that I have some matrix that I multiplied it before. I didn't show the other way, like if I tried to put the AB on the other side, but you can do these same tricks to show that you'll get IN as well. And then finally, for the third one, let's take a look at A inverse transpose and multiply to A transpose. Well, according to what we've done in the past, then I can reverse the order A times A inverse under a single transpose, but A inverse is the identity matrix. And of course, when you take the transpose of the identity matrix, the ones on the main diagonal do not move. Of course, there will still be zeros everywhere else. So that takes care of the third property. Note, you still need to show that B inverse A inverse times AB is the identity matrix, and A transpose times A inverse transpose also equals the identity matrix. You can use pretty much exactly the same steps that I did, but I'm going to leave those for you. Now we're going to spend the next several minutes taking a look at row operations and something called elementary matrices. There is a way to start with, take my matrix and I augment it with the identity matrix, and then go through row operations until you end up with the identity matrix on the left, and then on the right will be the inverse. And so what I'm going to do is use this to show you how to get an inverse for a matrix, and then I'm going to explain why that actually works. So let's do the example first. So as an example, let's compute the inverse of, and my matrix then, 1, 2, 3, 4, 5, 6, 7, 8, negative 9. So I'm going to start with A/I3 in this case. So let's go ahead and do that. And on the other side, I'm going to go ahead and put my 3 by 3 identity. Now what I'm going to do is use row operations until the left side becomes the identity. Just like you're solving a system of equations, no different. You're actually, I'll talk about it later, but you're actually solving 3 systems of equations all at one time doing this method. So the first things that we would do is we would take negative 2r1 plus r2 to wipe out the 2 in the first column. Now don't forget, you need to do exactly that same stuff on the other side of the vertical line. Well, let's move on. negative 8 plus 5 is negative 3. Negative 14 plus 8 is negative 6. And then negative 2 plus 0 is negative 2. And then to target this 3, I'll do negative 3r1 plus r3. So I'll get negative 12 plus 6 is negative 6. Negative 21 minus 9 is negative 30. And then negative 3 for this spot. Okay. Now the next thing I'm going to do is I'm going to prepare this 4 to be annihilated. Right now I'd have to introduce fractions to take out the 4. To avoid that, I'm going to multiply my first row by 3. I needed to do no such prep work on the last row because it was already set up to be annihilated. So let me go ahead and then use my negative 3 in the middle row here to take out the items above and below it. So I'll do 4r2 plus r1. And we know that nothing in the first column will be affected by any of the stuff that I'm going to do. So this negative 3 times 4 will wipe out that 12 up there. And then negative 24 plus 21 is negative 3. And let's see what happened on the other side. Negative 8 plus 3 is negative 5. 4 plus 0 is 4. And then I'm going to wipe out this negative 6 here and see what happens. So I will do negative 2r2 plus r3. So 12 minus 30 will be negative 18. And then I'll have 4 minus 3 will be 1. Then I'll have negative 2 plus 0 will be negative 2, and then a 1. Next, to try to make this negative 18 wipe out this column, I would divide by negative 18. Unfortunately, the other side prevents me from wanting to introduce such fractions. So I'll prep the other rows for that to happen by multiplying row 1 by 6 and row 2 by 3. Now I'll clean up the third column. Negative r3 plus r1. So I know what's going to happen in the first row there. And let me go ahead and finish this stuff up here. Negative 1 minus 30 is negative 31. And then I'll have 2 plus 24 will be 26. And then I'll have negative 1 plus 0 will be negative 1. And then I'm going to do negative r3 plus r2 as well. And so let's see here. Negative 1 minus 6 is negative 7. Then we have 2 plus 3 will be 5. And then negative 1 plus 0 will be negative 1. And the third row, of course, is unaffected. And now we're ready to finish it off. So I am going to take 1/18 of row 1. I'm going to do negative 1/9 row 2. negative 1/18 row 3. And let's see what we get. I get negative 31 over 18, 26 over 18, negative 1 over 18. And then for my second row, I'm going to get 7/9, negative 5/9, and 1/9. And then for row 3, I'll get negative 1 over 18, 2 over 18, negative 1 over 18. This thing here is our inverse matrix. I prefer to write it in the following fashion, though. I'm going to pull out the 1 over 18 and then just put the other numbers there because, you know, I guess it looks a little nicer. So I'll have negative 31, 26, negative 1. Now watch that second row. I got to multiply those numerators by 2 since I'm factoring out 18 and not just 9. So 14, negative 10, 2, and then my last row, negative 1, 2, negative 1. You can check that my A times A inverse is the same as A inverse times A, which is the 3x3 identity matrix. Next, let me talk a little bit about elementary matrices. Let's recall our 3 row operations. All right, the first one we had was to swap 2 rows. The second was to multiply a row by a non-zero number. And third was to add a non-zero multiple of one row to another. What we can do is we can invent matrices that will actually make these things happen when we multiply them to other matrices. Let me show you what I'm talking about. Here I'm going to work with 3x3 matrices. So one thing you should know is these elementary matrices are always square matrices. Let's go ahead and take a look at the swap 2 rows. So what you do is you start with the identity. So as I said, my example here is going to be 3x3 because it's robust enough to get the idea across, but it's also not so complicated as to make the examples I'm going to use horribly grisly. So let's start with what I call an E1. This is where I swap, say, rows 1 and 3. So if I wanted to swap rows 1 and 3, here's what it would look like after the swap. So that was a swap rows 1 and 3. Now take a look at what it actually does to a matrix when I multiply it on the left. So if I take E1 times a general matrix, and I won't specify any of the entries for A. I'll just write them in as generic items. Now when I multiply them, here's what happens. I will swap the third row with the first row in A. That'll be the effect. And once again, multiply any of these out that you think that you need to see the details, but there's nothing really fancy here. It will multiply out and see rows 1 and 3. Here's row 3 originally, here's row 1 originally. They got swapped, and that's because I was able to multiply on the left by that type of a matrix. So this guy on the left is called an elementary matrix. You can call it a swap matrix or whatever you want. But then let's go ahead and invent a second type, E2, which was to multiply any row by a non-zero constant. So we could do something like this then. Start with the identity, but then let's say we multiply the second row by some sort of a scalar, a non-zero scalar. So we multiplied, I multiply row 2 by k, and of course k is not equal to 0. This will actually equal, it will work if k equals 0. It's just you never really want to zero out a matrix. And plus, if you do multiply by 0, you'll lose the ability to perform an inverse. So let's take a look then at E2 times A. So if I take 1, 0, 0, 0, k, 0, 0, 0, 1 times a general matrix, what you'll get is the same matrix, except the second row will be multiplied by k. Okay? And then the third type is where I multiply one row by something, by some non-zero, although once again, it wouldn't matter if it's 0, except you would never do such a thing because it wouldn't do anything. Multiply one row by a non-zero number and add it to a second row. So suppose I started with the identity matrix, but then I multiplied row 1 by k and then added it to the second row. So this is k times row 1 plus row 2. And so now look at the effect. Well, I think you'll figure out what the effect is before I actually do the multiplication. I'll need a little extra space here. So everything's going to be the same except the second row will have k times the first row added to it. So my second row will look like k A11 plus A21, k A12 plus A22, k A13 plus A23. But then the rest, of course, are left alone. So we can use this left multiplication by elementary matrices to actually do the row operations for us. You'll see as we do the previous example using these instead to show you how it works. So I want to redo the last example. Compute the inverse, and the matrix was 1, 2, 3, 4, 5, 6, 7, 8, -9. And so let's start. Now basically, remember when we did the last example, I had the identity matrix on the other side of it. Well, the steps we use to whittle this down to the identity matrix on this side are no different than the steps I would use to solve the things anyways. So I'm just going to go through the same process. I'm going to try to get this matrix in the form, I'm going to try to use row operations to transform this matrix into the identity matrix. So let's revisit all those things that we did. And the first thing I did was take out the 2 that was underneath of the 1. So in order to make that happen, we need -2r1 plus r2. So let me call it E1 will equal it'll be that, -2r1 plus r2. And then when we take E1, you can check these things out. I will have done exactly what I said. It will look like this, 1, 0, and -3 there, and -14, -6 there. Next, I attacked that 3. So I did -3r1 plus r3. Now, what I want to do is try to stick with exactly the same things that I did before. And before, I didn't want to introduce fractions. Even though I don't have another side, I want to stick and do exactly the same things I did previously. So the next thing that I did was multiply the first row by 3. Of course, all that does is multiply the first row by 3 and leaves everything else the same. Okay, remember what my next step was. Now, you'll notice the one thing I can't do, I can't double up operations, although I probably could on these elementary matrices. Unfortunately, once you do more than one thing, they're no longer called elementary matrices. So elementary matrices are meant to do one and only one thing each time. Well, the next thing I did was targeted this 12 for elimination. So I did a 4r2 plus r1. You know what? I have not been keeping up very well here. When I've been doing this, I've been applying this E2 not to A, but to the previous matrix. So I probably should have been much more careful here. This is a matrix in progress, this is not applied to the same A. So for example, this would have been E2, E1A. Then this would have been E3, E2, E1A. And you can see as I go, I'm going to need more space then. So I'll have E4, E3, E2, E1A. Let's see what all of that is going to equal to. So I'm basically going to take out that 12. What do I end up with? 3, 0, negative 3. I'm going to have to scrunch my stuff in here a little bit. 5. The next thing I wanted to do was use this negative 3 to take out the negative 6. So that would be negative 2R2 plus R3. Let me see if I can make things a little bit smaller here. And then I have E5, E4, E3, E2, E1 times A. And once again, it would be tempting to use a fraction of this to wipe out the other things, but that's not what I originally did. So I'm going to keep going and doing one thing at a time. What I ended up doing was I multiplied the first row by 6 and then the second row by 3. Now I think what I'll do then, to save myself some space, E6, E5, and I'll go dot, 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 E1A. This one was simple. All I did was multiply the first row by 6. And then the next thing I did was multiply the second row by 3. And then I have E7 dot 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 E1A equals and then I went and cleaned out that third column. So only one step at a time. Once again, negative R3 plus R1. And then when I have E8 dot 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 E1A, that's 18, 0, 0, 0, negative 9, negative 18, 0, 0, negative 18. And I'll use exactly the same operation again to get rid of the other negative 18 in the second row. So we have negative R3 plus R2. And then E9 dot 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 down to E1A equals 18, 0, 0, 0, negative 9, 0, 0, 0, negative 18. And then the last three steps was to divide each row by the appropriate amount to make them into ones. I prefer to write E10 like this. No, actually I can't put on the outside because that would multiply to every item inside of there. So no, sorry about that. That was my bad. It has to look like this. And then if I have E10 dot 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 down to E1 times A, what would that be? 1 0 0 0 negative 9 0 0 0 negative 18. Continue. This time I'm going to do negative 1/9 row 2. So my E11 and then if I do E11 dot 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 E1A, well, I have 1 0 0 0 1 0 0 0 negative 18, and I'm ready to finish it off on this last step. Step 12, I will do negative 1/18 row 3. And then E12 dot 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 down to E1 times A will finish off the deal. And there we have it. So what we have then is we have E12 dot 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 E1 times A is equal to the identity matrix. And you don't really have to check the other way. We'll show that in a little bit. But one thing that you should know is that each of these matrices, these E sub I matrices, they're all invertible because they're just one step, and you can always reverse one step. So they all are invertible. Now this here then, all of this stuff, that is A inverse. So you can go ahead and multiply them all out if you want to, but you'll get exactly the same thing that we got previously. All right, here's some notes. When solving A/IN to IN/A inverse using the row operations, you're actually doing three things at once. Let me go ahead and put it here. You've got A11, A12, well, A31. I put the order of these items incorrectly. Now, any of the things that I'm speaking of here can be generalized to larger matrices, and you've seen the way we've treated larger matrices before. The steps aren't any different. It will just require an expanded notation. That is it. We are actually solving the following. We were doing A11, A21, A31. All at the same time. So each one of these we're able to do that. That is, we are finding AX1 to equal 1 0 0, AX2 to to equal 0, 1, 0. AX3 will equal 0, 0, 1. That way, we can do AX1. These will be columns of a matrix, X2, AX3, and that will equal 1, 0, 0, 0, 1, 0, 0, 0, 1. But on the left, I can factor out my A. And in this way, this thing right here is your A inverse, because A times that ends up being the identity matrix. I said it, but I think I'll reiterate it. Note, any elementary matrix is invertible. For example, remember if I had E was equal to where I swapped rows, let's say I swapped rows 2 and 3. Well, the inverse of that particular matrix is exactly the same thing. You swap them back, but it looks like the same matrix to begin with. So swapping is very simple. It's something that if you do it twice in a row, you've swapped and then swapped them back. So that's an easy one. On the other one, let's say I went and multiplied one of the rows by, say, a non-zero real number, say the first row in this case. Remember, to make this k is not equal to 0. You never want to just zero out a row. It doesn't do anything for you. The inverse of this then is simply this. And what was our last one, where we take a multiple of one row and add it to another row? So let's say I had 1, 0, 0, 0, 1, 0, but I multiplied row 2 by k and then added it to row 3. The inverse for this was a little bit strange. The inverse was identical, actually, in nature, except we would add the negative of row 2 to row 3, and that actually is the inverse. So each of these matrices is invertible. Another theorem. Let A be an n by n matrix. A is invertible if and only if it is row equivalent to I sub n. So if you're able to use row operations to transform A into the identity matrix, guess what? A is automatically invertible. Well, once again, it's an if and only if type proof, so there's two directions. The forward direction is the stuff that comes before the IFF. We're going to assume that A is invertible. Then, for any B in Rn, AX equals B has the unique solution X equals A inverse B. But since AX equals B has a solution for every B in Rn, we know that A has a pivot in every row. Look at 2 videos ago, I think I proved that particular statement right there. So we have a pivot in every single row. Well, let's think about this. N rows implies N pivots. But now, wait a minute then. Then N pivots and N columns. Remember, N or A is an N by N matrix. N pivots and N columns, since the pivots have to occur in different columns, implies that we have a pivot in every column. Thus, we must have an echelon form of A as follows. So I don't know what you want to call it. I usually use the letter U to indicate echelon forms. I have to have one in every single column. So I have to have one in column 1 and in row 1. Next I have to have one in column 2 and in row 2. Column 3 and in row 3, until I get to column N and row N. And I really don't care what's above there. Under there are zeros. Well, then it's easy. Then I can take this item, this non-zero item, and clean out all the items above it. I can take the next non-zero pivot that is to the left and up, left one and up one, clean out all the items above it, and just work my way backwards to make that a zero up there. Well, so after cleanup then, what I will get then is the identity matrix by doing those cleanups. So with that in mind then, so this implies that A is row reducible to the identity matrix. Oh, I think I misspoke. Just one thing. I can use this pivot to erase everything above it, but then before I finish up, I would have to divide by each of the pivot numbers so that I would have ones down the diagonal. And then I would eventually get to IN. Well, I think I said all that by not writing in here. I indicated all that by saying that I would eventually get to IN. Next, assume that A is row equivalent to the identity matrix. We saw how you can do this. I can do A can go to E1A using row. These are just row operations. E2, E1A. And I can use as many row operations as I want, used instead as multiplying by these matrices instead of actually doing them using left multiplication by these matrices, until I eventually get to something like this. And so we knew that it was row equivalent to IN, so I can use those matrices. But then what you have is that EP down to E1 inverse times EP E1A equals EP E1 inverse times the identity matrix. So we get A equals EP dot 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 down to E1 inverse. And in fact, we know that the product is invertible because the inverse of this particular matrix, if you multiply it out, is the following: E1 inverse, E2 inverse. It's the inverse is in reverse. So we already knew that the product was going to be invertible, and we already knew that the inverse of a product is the product of the inverses. Suppose AB equals AC, where A is n by n, but B and C are n by p. If A is invertible, then we can do the following. I can multiply both sides by A inverse. And then regroup to get that B is equal to C. So when A is invertible, we can cancel it, just like you would with real numbers. Note, AB equals AC can happen where B does not equal C when A is not invertible. In fact, you can probably play around and come up with matrices that are not zero, where AB is the zero matrix, then AC is some other matrix, and then B and C, of course, not being the same thing. Suppose that A and B are n by n matrices where B and AB are invertible. Show that A is invertible. Suppose AB equals C. We know that C is invertible. We're told that A times B is invertible. Also, I could multiply both sides by B inverse like the following, and then regroup the left side. We're also told that B is invertible. So now what we have then is that A is the product of invertible matrices. Since B inverse is invertible and C is invertible, those were both given. Well, the B inverse wasn't given as invertible, but we already showed in the previous theorem that if B was invertible, B inverse is also invertible. And a previous theorem also showed that the product of invertible matrices is invertible. So A is the product of invertible matrices, so A is invertible. Example, let B and C be invertible matrices. Does the equation C inverse A plus suppose that I have that equation there. Does the equation have a solution for the matrix X? Well, let me start with that equation again. First thing I'll do is multiply on the left by C. And so I have A plus X, B inverse equals C. I'll multiply then on the right by B. And then finally, if I want to figure out X, I'll subtract A. Notice though that the CB has got to be in that order in order for this to be a correct solution. Suppose A is an invertible n by n matrix. Show that the columns of A are linearly independent. So I'm going to let A equal A1 dot 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 up to AN, like so. And suppose x1 up to xn are all real numbers such that x1a1 plus dot 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 plus xnan is equal to the 0 vector. Remember, then, we want to show that the x's are all 0. So we can redo this in terms of a1 dot 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 an times x1 dot 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 xn, and that equals the 0 vector. Let me change to a more suitable notation for this, or at least a simpler notation. Now I know that A is invertible, so I can multiply both sides by A inverse. Of course, the left side I can regroup. Of course, any matrix times the 0 vector is 0. And so then I'll get INX equals 0, but INX is just x. And that means that x1 equals x2 equals dot 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 equals x sub n, and all of those numbers were 0. So therefore, the columns of A are linearly independent.